Hello everyone, this is Dr. Lennon, and we are going to do local extrema today. So this is one of the big applications of the derivative. So let's recall from looking at some of our basic functions and understanding the graphs of them, how the derivative related to properties of a function and also the second derivative, what that said. So let's recall, so let's suppose f is a differentiable function. So just meaning that you can actually take the derivative of it. Things that have lots of sharp corners and cusps might not necessarily be differentiable. So if the first derivative is 0, or is greater than 0, is positive on some interval, then that's true actually. We can say if and only if. That's a little bit stronger than then. So that's if and only if f is increasing on I, and analogously the first derivative is negative on some interval I, just meaning some interval of input values x, if and only if f is decreasing on I, and then we also had some information about the second derivative. So if you take the derivative of the function and take it again, that's known as the second derivative. So the second derivative is greater than 0 on some interval I, if and only if f is concave up on I, and the second derivative is less than 0 on some interval I, if and only if f is concave down on I. So we looked at these when we talked about sketching graphs of derivatives, but just to remind you what concavity means, we could look at some function, maybe like a cubic function. So let's say we have some function, that perhaps looks like this. Okay, we've got something like that. So notice it has kind of this like downward U shape until about here, this value that I marked with an X, let's say that's value A, and then afterwards it's an upward U shape. So that point X, we would say an inflection point, so that's a place where concavity changes. At x equals A, and 1, so I don't know, let's give this function a name, let's call it f of x. So f of x is concave down for x values less than A, so that's the interval. So to the left of that x, we have a downward U shape, and the second case, we would say f of x is concave up for x greater than A. So just to remind you what concavity means, increasing and decreasing, I think most people are familiar with. Increasing means the graph is going up as you move to the right, and decreasing means the graph is going down as you move to the right. So one of the things the derivative is going to do is it's going to allow us what already tells us when the function is increasing or decreasing, and we can use this information to figure out where some local extrema occur. That's the title of this section, after all. So let's first write a definition about a critical point. So what is a critical point? So if f is a differentiable function, a point, or we'll say a point. When I say a point, I really just mean the x value here. That's what I'm talking about. A point x equals p is said to be a critical point or a critical value. We'll say critical value since it's just an x value. So maybe I'll switch from point to value. It's a little more consistent. So it's said to be a critical value if either f prime of p equals 0 or f prime of p is undefined. Most commonly for us, it's just going to be f prime of p is equal to 0. So that's going to be a critical point. So the first derivative test basically tells us what happens. And the whole idea of the first derivative test, so the idea comes from this picture. So if you look at a picture and we look at a local extreme value, so let's look at something similar to the picture we just drew. So a local max looks like the top of a hill, and a local min looks like a top of a valley. So notice they're not an absolute max or a global max or min because they're not the biggest y value that you see on the graph. They're just kind of like the biggest or smallest guy in some neighborhood of that point. So this point, if we labeled it, say, capital A, and this point, say, we labeled it capital B, A is a local max because it's the biggest point in some small neighborhood, and capital B is a local min. So the first derivative test shows us if we have some formula and we're trying to identify these points. Well, we can do that by basically looking at the derivative. So first of all, notice that both of these are going to be critical values for a function because, the tangent line at those points is horizontal, which means the derivative is 0 there, so those are going to be critical values. And furthermore, the function changes from increasing to decreasing at A and from decreasing to increasing at B. So the first derivative test basically tells us if we can analyze around those critical points, we can figure out whether or not they're maxes or mins by just dealing with the derivative formulas. So this is the first derivative test. It's one of the great tools of calculus that we use all the time. So we suppose, again, that f is a differentiable function, and p is a critical point of f. So there's two kind of conclusions here. One if you have a local max and one if you have a local min. So if f prime changes from negative to positive at p, then f is a local min, or f has a local min at p. So that's what's happening at the graph above. Basically, the derivative tells us whether or not the function is increasing or decreasing, and that tells us whether or not we have a local min or local max. So understanding something about the derivative is helping us understand information about the graph of the function. So that's what really quite powerful that way. And then we can say if f prime changes from positive to negative, at p, then f has a local max at p. So let's look at some examples about how we can use this first derivative test to identify local extrema. So usually what this amounts to is we're going to know some derivative formulas. We're going to have to set the derivative equal to 0, solve, and then we're going to use what I call test value regions to figure out the value of the derivative in those different spaces. So let's look at an example. So we'll say use the first derivative test to find any local extrema. So this first function we're going to look at is f of x is equal to x cubed plus 6x plus 1. So let's kind of write this one down in detail. So step 1 is take the derivative. Step 2 is set to 0 and solve for critical points or critical values. Step 3, we want to use test value regions to identify where the derivative is positive or negative. And then 4, use the first derivative test to identify local extrema. So this is our big strategy. So pretty much all the problems go through this, but you kind of have to get used to how we write it down and set things up. So for us, step 1 is pretty straightforward. So step 1, we want to take the derivative. So f prime of x is equal to 3x squared plus 6x. Oh no, plus 6. The x goes away. So just using the power rule for a polynomial. So step 2, we want to set that equal to 0 and solve to get our critical points. So we have 0 equals 3x squared plus 6. So one second here. I think I may have made a mistake. I think perhaps I wanted x cubed plus 6x squared. So let's go ahead and adjust that. And the reason I'm saying that is the way it's working out, we're not going to end up with any critical values. So let me adjust this problem a bit. So let's change it from f of x equals x cubed plus 6x to x cubed plus 6x squared plus 1. And then our derivative will be instead 3x squared plus. Now when you take the derivative of x squared, you would get 2x, and 2x times 6 is 12x. So we're going to have 3x squared plus 12x. So sorry about that typo. So now we have something reasonable to solve. So we can solve just by factoring. So we can take out a 3x, and we have x plus 4. So again, this is a quadratic, so solving that just amounts to writing either 3x equals 0 or x plus 4 equals 0, which is just the value x equals negative 4. So over here we have x equals 0. So these are our two critical values that we're using, x equals 0 and x equals negative 4. So these are our critical values. So step 3, how do we use that to break up the to use what I called as test value regions? Well, if you look at all possible x values, that's just the number line. So you can just write 2.0 and sorry, actually we want negative 4 to come first. That's the smaller of the two numbers. So negative 4 and then 0. Notice that aside from those two numbers, you can kind of split up the real number line into 3 parts. Part 1, part 2, and part 3. So what you want to do is you want to plug in any old point from each of the regions to test the sign of the derivative there. Now the derivative either has to be completely positive or completely negative in any of those regions. It cannot change until it passes through one of those critical values. So you only need to test a single point. So let's say region 1, we want to test some point. Well, maybe you have some scratch work over here, so we just need to test a single point. So let's do region 1 are the numbers less than -4. So let's just do f of -5. And f prime of -5. We're testing that all the way back up here in the first derivative. So we're plugging that in there. So what does that come out to? Well, we can just type that into our calculator. So if you do 3 times -5 squared plus 12 times -5, we end up with positive 15. So in that first region, that means f prime is positive. So f is increasing. So that's basically what we need to figure out. Is f increasing or decreasing in that interval? Because we're using that information to determine whether it's a max or a min. Okay, then I need to pick a number from the second region. So any old number inside 2. So maybe -1. -1's a reasonable number. You can't pick -4 or 0 because those are your critical values. Again, plug that way back into f prime of x. So if you do that and you plug it into your calculator, you end up with -9. So in region 2, we have a negative first derivative. So that means f is decreasing. And then in the third region, we can plug in, again, any number bigger than 0. So let's say f prime of 1, that will come out to positive 15. So in region 3, we have f prime greater than 0. So f is increasing. So now we can form our conclusion. So step 4, what is the conclusion? So the conclusion is by the first derivative test, f has, well, 1 we're increasing, 2 we're decreasing. So if we scroll back up to the first derivative test, if we change from negative to positive, then that means it's a local min, and from positive to negative, a local max. So what did we do? We went from positive to negative. So our first point is a local max. So f has a local max at x equals -4. And what happens at the second point, 0. So from 2 to 3, we go from negative to positive. So that means that we have a local min. So, and at x equals 0, f has a local min. So that's where those absolute or local max and local mins occur. If you want to figure out precisely what their values are, you need to plug them back into the regular function. So let's go ahead and do that quickly. So let's remember what our regular function was. Our regular function was x cubed plus 6x squared plus 1. So if we do f of -4 and we plug that into the calculator, we would do -4 to the third power plus 6 times -4 squared plus 1. Okay, so this comes out to 33, so that tells us our local max. It has coordinates -4, 33. And we can do the same thing with the local min that we found. We can go ahead and plug in the other value 0. And that's easy because that just gets rid of all the x cubed and 6x squared terms. So f of 0 comes out to 1. So our local min is 0, 1. Okay, so let's look at another example. Perhaps we won't have... we won't go through all the steps in as much detail. We won't explicitly partition them, but we'll still find the maxes and mins. So let's look at a function g of x equals e to the x minus 10x. So step one, we want to take the derivative. So g prime of x is e to the x minus 10 using the exponential rule on e to the x and the power rule there. So we want to set this equal to 0 and solve. So 0 equals e to the x minus 10. Add 10 to both sides. So we have 10 equals e to the x, and then we can take the natural log of both sides. So the natural log of 10 is e to the x, is the natural log of e to the x. And I'm okay if you just use a decimal approximation here. So the natural log of e to the x, so that just comes out to x on the right-hand side. And the natural log of 10 is probably about 2 point something, so that's about 2.30 if you round to 2 spots. So we only have one critical point here, so that means our interval is just divided into 2 parts. So we have this value 2.3. We have 2 regions. So again, we just want to plug in a point into each region and form the conclusion. So let's say f prime of 0. Again, we're plugging that into the derivative. So, sorry, not f, we're using g for this part, so it would be g prime of 0. So plugging that value into the derivative, g prime of 0. So we're plugging it in over here into g prime of x equals e to the x minus 10. So that would be 1 minus 10, which comes out to negative 9. And we want to plug out in something on the other side, say g prime of 3. That's a value in region 2. So if you do e to the third power minus 10, that comes out to 10.09 about. So basically, region 1 is negative, so g prime is less than 0. So g is decreasing. And in region 2, g prime is greater than 0, so g is increasing. So from the first derivative test, if you're changing from decreasing to increasing, then you have a local min. So a local min for g occurs at x equals 2.3. And we could say, and if we say and has value, that means we're trying to plug the x value into the original function to figure out what the corresponding y value is. So regular g of 2.3, if you plug that into the original function e to the x minus 10x, let's use our calculator to figure out what that is. So e to the 2.3 minus 10 times 2.3 comes out to negative 13.03 if you round to 2 decimal places. So that is the local min has coordinates 2.3 comma negative 13.03. So those are the values there. Let's look at another one. Let's say C. Let's say h of x equals x times the natural log of x. And again, we're only considering this function for positive values. That's the domain of the natural log of x. So if we're trying to find the derivative here, so let's note to find h prime of x, we need to apply the product rule. So how do we do that? We let u be x, we let v be the natural log of x. So u prime is equal to 1 and v prime is equal to 1 over x. So we can use that. So h prime of x should be the natural log of x plus x times 1 over x. So h prime of x is the natural log of x plus 1. So what we want to do is set that equal to 0 and solve to find our critical point. So subtract 1 on both sides. So we have -1 equals the natural log of x. And then remember, to undo the natural log of x, you need to make both sides of the equation the exponent of e. So e to the natural log of x cancels out, and you just get x. On the other side, you get 1 over e, and 1 over e is 0.37 if you round to 2 spots. So again, we've just got one critical point, so we're dividing our number line just by this 0.37. So we only have two values, or two regions, 1 and 2. So again, for region 1 and region 2, we want to plug in some numbers. So maybe we can plug in, and here's the trick actually. So I've made a bit of a mistake here. We really don't want to have that number line going on forever and ever and ever, because we said x is only allowed to be positive values in our original domain, remember at the beginning. So for region 1, it's actually between 0 and 0.37. If you look back up here, remember that this x has to be greater than 0, so that's going to come into play. So when we plug in our numbers, I don't know, for region 1, we could plug in something like f prime of 0.1. Again, we need to plug this into the derivative. So the derivative function is the natural log of x plus 1, all the way back there, h prime, and I'm using f again, I should be using h, I'm sorry. So we need to delete that f and make it an h. So h prime of 1 is, again, the natural log of 0.1 plus 1. So this comes out to negative 1.30. So we get that h prime is less than 0, so h is decreasing. And then let's plug in a point from region 2. Anything positive will do. H prime of 1, not anything positive, sorry, any positive value greater than 0.37. So this comes out to the natural log of 1 plus 1. Natural log of 1 is 0, so this actually equals exactly 1. So in region 2, h prime is greater than 0, so h is increasing. Again, we're changing from decreasing to increasing, so that tells us that this is a local min. So h has a local min at x equals 1 that has value h of 1, and our function was just 1 times the natural log of 1, and the natural log of 1 is actually equal to 0. So basically, the local min is 1, 0. Again, a lot of times if you want to, keep in mind that we can go ahead and actually just graph these things to see if what we did makes sense. So let's go ahead and just do that here. So our function, we said h of x was equal to x times the natural log of x. So if we graph that, we see we get this value here, and we said our local min was at x natural log of x, we're getting 0.368, negative 0.368. So something seemed to go wrong. What happened here? X natural log of x 1, 0. So did anything, well, our critical value is 0.37. I don't know why I wrote down x equals 1. Well, that's a good reason we checked this one with a graph. 1 was the last number I plugged in. That was just stuck in my head for some reason. So it has a local min at about 0.37, and we want to plug that into h. So yeah, I botched that up. I do apologize. So we have h of 0.37. So that's going to be 0.37 times the natural log of 0.37 when you plug that in. So let's see what we get on the old calculator. So we get negative 0.37 about. Again, I'm just rounding to 2 decimal places. So that tells us the local min has coordinates 0.37 comma negative 0.37, and that looks correct when we go back to our graph. So if we go back to the graph here, this is the bottom point, 0.37, negative 0.37. Again, they have a little more accuracy. They're using 3 decimal places rather than 2. So let's go ahead and go back and do one last example. So part D, why don't we do, let's do one more that requires a chain rule. So let's say D, let's say we have f of x is x times e to the minus 3x. So again, we're going to use a product rule here. So note, we need to use the product rule. So the product rule, again, our first coordinate here, u is x, and v is e to the minus 3x. So u prime is just the derivative of x, which is 1. V prime, we're using our continuous exponential derivative rule, which is negative 3e to the minus 3x. And then our derivative here is going to be f prime of x equals e to the minus 3x minus 3x e to the minus 3x. So we want to set this equal to 0 and solve. And we can do that by factoring. Both terms actually have a common factor of e to the minus 3x. So we can factor that out, e to the minus 3x. So we'll have a set of parentheses. And then on the inside, there will be 2 terms. So 1 times e to the minus 3x is e to the minus 3x, and we get minus 3x on the inside. So let's, again, just make a comment. So note that e to the minus 3x is greater than 0 for any value of x. So the only thing that can be 0 is what's in the parentheses right here, 1 minus 3x. So 0 equals 1 minus 3x. We can solve that, and we get 1/3 is equal to x. So you just add 3x and divide by 3, so x is equal to 1/3. That's our only critical point for this problem. And again, we just set up the test value regions. Again, we have a single value here. So we have 1/3, and then we have 2 regions, region 1 and region 2. So we want to figure out what the derivative is doing in each region to determine if we have a max or a min. So in the first region, we want to plug in some value less than 1/3. Again, we have no domain issues here, so let's suppose we plug in... Oh, you know what? Actually, we forgot about one thing here. We do, in fact, have 2 critical points. Why do we have a second critical point? Well, there is a domain issue here. So what is that domain issue? This e to the negative 3x, this component, if we look at the other part, e to the negative 3x, so if we rewrite this as 1 minus 3x over e to the 3x, no, that actually doesn't turn out to be an issue. So the one thing I was concerned with was maybe e to the 3x is undefined. But again, since that's always greater than 0, we're never dividing by anything greater than 0. So we don't, in fact, have a problem there at all either. So we don't have to worry about that. Remember, one of the parts of the definition was perhaps the the function's not defined, but that doesn't turn out to be the case here. So let's just plug in 2 points, one from each region, and we'll determine whether or not our function is positive or negative. So in region 1, we need to plug in some x value less than a third. So our derivative function is e to the negative 3x minus, so f prime of 0, let's say 0 is always an easy one to plug in. We're going to end up with e to the 0 minus 3 times 0, e to the 0. Well, so the second term goes away, but the first e to the 0, so this is just 1 minus 0, which equals 1. So in region 1, f prime is greater than 0, so that tells us f is increasing. And in region 2, we want to plug in something bigger than 1/3, so let's say we want to do f prime of 1. So that's going to be e to the first power minus 3 times 1, e to the first power. So what does that come out to? That's going to come out to something negative. It's actually going to come out to minus 2e. So that is negative 5.43. But that's all we care about is if it's positive or negative. So in region 2, we see that f prime is less than 0. So f is decreasing. Since we're changing from increasing to decreasing, that means we have a local max. And again, you can plug the value in 1/3 to figure out what the y value is, which is about 0.12 here. So we see that f of 1/3, 0.12, is a local max. So we have a local max right there. Okay, so give these a try. Again, there's a lot of steps, but it just comes down to practicing and organizing your information. A lot of different derivative rules that can come up, so going back and making sure you're using the appropriate rules based on the class of functions, or product rule, quotient rule, or chain rule, which we've all just gone over, is going to be pretty important here. So if you have any questions, I encourage you to send me an email, and I will be sure to go over those. Otherwise, stay safe, and this is Dr. Lennon signing off. That comes out to 33.